So hello everyone, this is Abhishek Verma and today I am going to discuss a lead code problem, primes in the diagonal. So in this problem you have given a two-dimensional array and we have to return the maximum prime number which lies on the diagonal, means on any diagonal. We have two diagonals, so the number must be lies on any of the diagonal and it must be prime. So we have to return the maximum prime number among all the numbers. So now the question is, what is a prime number? So for prime number are those number which are divisible by 1 or the number itself, and yeah, it must be greater than 1. So prime number are those number which are greater than 1 and they have only two factors, 1 and the number itself. So it is given in the question also. So now we have to return the maximum number which is prime and lies on any of the diagonal. So let's take the first example. So this is 1 2 3 5 6 7 9 10 11. So yeah, so let's take this example. Means in this example we have given an 2D array. This is 1 2 3, then 5 6 7 and 9 10 11. So now first we have to check only on diagonal elements. So 1 6 11 9 6 and 3 are the diagonal elements, and among these numbers 3 5 and 11 is the prime number. So we have to return the maximum among these numbers. So of course 11 is the maximum, so we have to return 11 as the answer. Okay, so the question is very simple, means we have to just check for all these numbers and we have to return the maximum prime number which lies on the diagonal. So let's see the code and try to understand the problem more. So yeah, so what I'm doing is I'm just running two for loops which checks for each and every element. So first I'm checking whether it is a diagonal element or not. So if I is equal to j, that means of course it is a diagonal element because I and j both are same, like 1 1 2 2 3 3. So this is a diagonal element. Or j is equals to n minus I minus 1, means this is the left diagonal. So first I'm checking whether it is a diagonal element or not. After that I'm checking whether the number is prime or not. Means there are two conditions. The first one is it will lie on the diagonal, and the second one is it must be a prime number. So first I'm checking whether the number lie on the diagonal or not. Then I'm checking whether the number is prime or not, means is prime function. Here we have a is prime function, and this function return me true or false. If the number is prime, then it returns true, otherwise it returns false. So after that I'm just storing in answer maximum among all these numbers, all these prime numbers, and I'm returning the answer as the answer. So now the question is how to check whether a number is prime or not. So as I told you earlier also, prime numbers have only two factors, 1 and the number itself. So I am checking if, see, 1 is not a prime number, so I'm declining 1 here also, means if nums of ij not equal to 1, because 1 is not a prime number. So that's why I'm checking for all those numbers which are greater than 1. So I'm running a for loop from 2 to I cross I is less than equal to n. So this line is very important, means I'm explaining it more. So sorry. So yeah, so let us suppose I have any number. Let us suppose I have a number 25, or let us suppose I take another number. Let us suppose I have a number 4. So if 1 is one of its factor, then the another factor is 24. And if let us suppose 2 is the factor of 24, then 12 is the another factor. And if 4 is one of the factor, then the another factor is 6. So now what I'm saying is any number n can be written as root n into root n. So if I increase any other side, then we have to decrease one of the sides. Means it for all the number, it is must that one of the factor lies, which one of the factor of the number is less than root n and other is greater than root n. It is must for all the number. If you see this example also, then if one of the factor is 1, then another is 24. If one of the factor is 2, then another is 12, because 12 into 2 is 24. And if one of the factor is 4, then another is 6. So it is must for all these number. If one of the factor is less than root n, then another, definitely the another factor is greater than root n. So this so that's why we have to reduce the time complexity to big O of n to big O of root n. And there is one specific case. Let's take an example of 9. Or yeah, let's take the example of 9. So now if 1 is the factor of 9, then 9 is also factor of 9. Now the another is 3. So 3 and 3 both are common because in both the side 3 and 3 lie. So that's why I'm running a for loop till root n. Means here equal to sign we must include I into I is less than equal to root n, because if one factor lies in this side, then another one must be there in this side. So we have to just check for root n, not for all the numbers n. So that's why I'm running a for loop till root n, and if we got any of the factor, then I'm returning false, otherwise I'm returning true. So yeah, that's it for the problem. Thank you.